And what I want to do today is start covering evolutionary fitness. Make sure that that's all visible on the screen. And we talked a bit about it yesterday, just trying to introduce the concept that fitness in the evolutionary sense does not necessarily have anything to do with physical fitness. It does not necessarily have anything to do with being mean or savage. All it is a measurement of differential reproductive success. And it applies only to genotypes. There's no way in which one person is more fit than another. All you could ever say is that all people or fruit flies or whatever we're working with that have one genotype on average have more offspring than all people or fruit flies, etc., with a different genotype. So fitness is not the kind of thing an individual has in evolutionary biology. And we'll start with practice problem number 6, which talks about a selection experiment on a laboratory population of good old Drosophila melanogaster, the common fruit fly, otherwise known as, I missed that one banana when I was cleaning the kitchen and now we're completely infested. And one of the alleles, or one of the genes in fruit flies is called stubble. There are two, it's a gene with 2 alleles, stubble and non-stubble. Flies that are heterozygous for the stubble gene have stubbly bristles. Flies that are homozygous for the normal gene have normal bristles. Flies that are homozygous for stubble die during development. It's what we call an embryonic lethal. So he starts out with 86% normal flies and 14% stubble flies. So let's go over here to the whiteboard. All right. There's the whiteboard, and we start with what I wanted there. Start with moving the toolbar. And we start with, use a nice big font. Flies that are homozygous for the dominant stubble allele that's an embryonic lethal, and those flies are never born. They don't exist. Heterozygous flies have stubble bristles. And homozygous recessive flies, and we start with a population of 86%. Check me real quick. Is that 86% stubble flies or 86% normal? 86% normal flies. And of course, 14% one percent. Okay, I'm going to turn the room lights on. I'm sorry if it makes this a little bit more difficult to read, but I can't see what I'm typing. And that should be legible, yes? Okay. Okay, so the first thing we got to do is calculate the allele frequencies. Now, we don't know the actual population size, but it doesn't really matter. We can pretend, if you want to, that The easy way to do it is just pretend that the population consists of 100 flies. That it's 86% normal flies and 14%, or 86, come on, Wagner, 86 normal flies and 14 stubble flies. Okay. So we'll take the frequency of the big S stubble allele, and we'll call that P. Okay, what's that equal to? Well, we have, how many flies have 2 copies of that? Well, the answer is 0, right? So we have 0 flies who have 2 copies of that allele. And we have 14 flies who have 1 copy of that allele. Right? All right. And the whole thing is divided by 200, because if we have 100 flies, we have 200 alleles, right? Okay, so that's basically 14 over 200, which is 0.07, I do believe. Anybody who wants to check my work can do so, but I think I'm pretty confident with 14 over 200. And then the frequency of the normal allele is going to be Q. And the easy way to do this is that if you have 2 alleles, then the frequencies must add up to 1. So if you have 2 alleles and the frequency of one of them is 0.07, the frequency of the other is 1 minus 0.07, which is 0.93. All right. If you want to do it the hard way, then we have 86 flies that have 2 copies of the normal allele. And we have 14 flies that have 1 copy of the normal allele. And if we divide the whole thing by 200, I don't have a calculator handy, but I am reasonably sure that that should come out to 0.93. Okay, I don't really care how you get the number. If you want to do it the long way round, because that helps you conceptually remember what it is you're doing, that's fine. If you want to do it the short way round, that is also fine. You know, like we say, you know, any way you want it, that's the way you need it. Yes.
It doesn't say like how much the population is.
Mhm.
Okay.
Okay, the really short way is that if all you've got is percentages, then the frequency of each allele is the frequency of homozygotes plus half the frequency of heterozygotes. So I didn't tell you that because I didn't want to give you another formula. And you can do it the long way around if you want to, but notice here that the frequency of the big S allele is equal to the frequency of homozygotes, which is 0%, plus half the frequency of heterozygotes, which is half of 14%. And of course, it works the same way for the other one. So if you just want to remember that the frequency of any allele is the frequency of the homozygotes plus half the frequency of the heterozygotes, that works. Or you can do it this way, which is longer, but maybe breaks it down a little bit more. You know, any way you want it, that's the way you need it. Sorry, it's kind of a reflex. Yes.
So I did, like I started with 0.86 and then considered that my p squared, like it's almost like it's SS, and then square root and then found p and then you times p.
Okay, hang on. So you started by taking that 0.86 and assuming that's equal to p squared, and then you take the square root and that gives you p. that only works if the population is in Hardy-Weinberg equilibrium. There are times when you might have to make that assumption. We were assuming that when we did that practice problem with the Hopi. Here we don't need to make that, well, for a big reason that you'll see in a minute, that assumption is almost certainly wrong. Gesundheit. For another reason, we don't need to make it because from this type of data, we can calculate allele frequencies directly. From the Hopi data, we couldn't calculate allele frequencies directly because we couldn't tell homozygous dominant individuals from heterozygous individuals. Here we can, because heterozygous individuals have stubble and homozygous dominant individuals don't exist. And it's fairly easy to count the number of things that do not exist.
That's my answer, but I guess it won't work.
In this case, no. All right, now if the population already is in Hardy-Weinberg, it'll work. And if the population is, and if you don't know, you can assume it's in Hardy-Weinberg equilibrium and try to take it from there, but then your answer is only going to be as good as whether your assumption is correct or not. If it's not correct, you won't get the right answer. And here, you don't need to make that assumption because we've got enough data that you can calculate allele frequencies directly from it. Okay, so that is part one. Yes. Okay, if you're counting alleles, you multiply by 2, because in a population of 100 flies, we've got 200 alleles. All right. Now, this would actually get complicated if we were working on some weird population, probably of plants that was tetraploid or something like that. Because that can happen. Plant species can end up with downright goofy chromosome numbers. That's actually what Dr. Noyes works on, if you know him and you're curious. Ploidy levels in plants can be oddball, but as long as you're working with a diploid species and assuming it's not a sex-linked gene, then everybody's got 2 of each allele. So that's when you multiply the denominator by 2. You're counting frequency of alleles. Because there are 14 flies that have 1 stubble allele. So you think about, think about what we're doing, why we're setting this up this way. This 0 times 2, that's the number of flies that are homozygous dominant times 2, because each fly has 2 copies of each gene. So we have 0 homozygous dominant flies who have 2 copies of each allele. And we have 14 heterozygous flies who have 1 copy of each allele. So this 0 times 2 plus 14 times 1 is the total number of alleles in the population that are stubble. And we divide that by 200 because 200 is the total number of all alleles in the population. And then down here, we've got 86 of our flies have 2 copies of the normal allele. So that's 86 times 2 normal alleles. And then to that, we add the 14 flies that have 1 copy of each allele. That's 14 times 1. And so 86 times 2 is going to be what? 172 plus 14 is going to be 186 total. We have 186 total alleles that are normal. Divided by 200, that's the total number of all alleles. So yeah, we're just dividing number of alleles by number of alleles. And Help me out, you're still kind of looking at me like I've just swallowed a live weasel. What, help me do this another way so I can make it clearer.
So it says 2 each for little, but they're like the same.
Okay, yeah, every fly's got 2 copies of every gene. I mean, except for sex linkage, but leave that out right now. Every fly's got 2 copies of each gene. The 2 copies can be the same, which means the fly's homozygous, or they can be different alleles, which means they can be heterozygous. Remember, alleles are variant versions of the same gene. So every fly's got 2 copies of the gene for bristle shape. And that gene comes in 2 versions, stubble and non-stubble. And so we have 86 flies that have 2 copies of the normal allele of the bristle gene, and 14 flies that have 1 copy of the normal allele for the bristle gene. Is that helping, or am I just making it worse at this stage? Okay, all right. This is why, make sure you all go back to your genetics class and make sure you're up on this. I would not want to see it's happened, but I would not want to see anybody crash and burn because their foundation of basic Mendelian genetics is wobbly. I'll help with that as much as I can, but you might need to go back behind the woodshed and dust off your old notes. Okay, right. Let's quickly go. Okay, let me find the screen share button. And go back to the practice problem. Okay. B and C get tricky because we got to start calculating fitness. Assume for the moment that wild type and stubble flies don't differ in fitness. Use the allele frequencies to calculate mean fitness. Okay, how do we do this? Fitness is a number between 0 and 1, and every genotype has its own fitness. All right. And fitness is the relative probability of reproductive success attached to each genotype. So let's go back to our whiteboard. All right, I'm going to erase that. And we represent fitness with a lowercase letter w. Not unlike that. Sure. Lowercase w. And we have to calculate fitness values for each one of our possible genotypes. So how do we do that? Fitness values are probabilities. So what is the probability of a big S fly having offspring? The answer is 0, right? Because big S flies are never born. I guess the eggs don't even hatch. So whatever the case, the fitness of big S flies is going to be 0. All right. Now, the only thing we know about the other flies is that their fitnesses are the same. So the fitness of stubble flies is going to be the same as the fitness of normal flies. Well, these are relative probabilities. So what we could do is we could observe a bunch of flies and say, okay, if you are a stubble fly, you have a 75% chance that any one of your offspring will survive. If you're a normal fly, you have a 75% chance. They're the same probabilities. Because they're the same, it doesn't matter what we make them. We can just call them X. It doesn't really matter what they are. Because what we're going to do is take our probabilities and divide them all by the highest value. Yes?
But what if the normal flies have a 100% chance that their offspring surviving? The heterozygote have 75% chance. Two heterozygotes.
Okay, okay, good point. I see what you mean. No, that's not quite the same thing. We're basically talking about the probability of a stubble fly reproducing versus a normal fly reproducing. And it doesn't matter who they're reproducing with. All right. So all we're told right now is that there's no difference in reproduction between a stubble fly and a normal fly. So we're just going to call that X. But what we do is we divide each of our three numbers by the highest of the three. So we don't know what X is, we don't care, only that it's a number bigger than 0. So our normalized fitnesses are going to be 0. 0 divided by X is 0. And 1 and 1. All right. Now what? Okay, if there is no natural selection going on, then we're in Hardy-Weinbergville. And if we are in Hardy-Weinberg land, then the frequency of homozygous dominance is going to be p squared. And the frequency of heterozygotes is going to be 2p cubed. And the frequency of the other homozygotes is going to be 2 squared. And those all add up to 1. Yes? That's the way we go if we are in Hardy-Weinberg land. The problem is that we're not in Hardy-Weinberg land because we have fitness going on. So the equation that we need here is going to be p squared multiplied by the fitness of the corresponding genotype plus 2pq multiplied by the fitness of the corresponding genotype plus q squared multiplied by the fitness of the corresponding genotype close those parentheses, is equal to something that is no longer 1. It's equal to mean fitness, which we write as W bar. W with a bar written over it. So that's our mean fitness.
So if you said that if we're not in Hardy-Weinberg, but if it tells us to assume, then are we ever going to be finding fitness, or is
Yeah, if you assume you're in Hardy-Weinberg, you don't even have to plug in these fitnesses.
it doesn't do like?
Because if you're in Hardy-Weinberg, by definition, that means you don't have selection going on, which means that all of your genotypes have equal probabilities of reproducing. Think about it. If all 3 of these genotypes had the same probability of reproducing, all their fitnesses would be 1, and these W's would just drop out.
We don't want to die.
Yeah, but if there's natural selection going on, that means some genotypes have lower chances of reproducing than others. Okay, you with me there? All right. Okay, let's back up a little bit. How can I make this more clear? Okay, If we're in Hardy-Weinberg, by definition, that means no natural selection. No natural selection just means that every individual, no matter what their genotype is, has an equal chance of having babies. All right? And if every individual has an equal chance of having babies, that means these fitness values all just become 1. Right? They all become X over X, which is 1. All right. And then if you plug those into this equation right here, they would all just drop out, because if they're equal to 1, then of course, p squared times 1 is just p squared. They'd all drop out and you would have a simple Hardy-Weinberg identity. P squared plus 2p cubed plus q squared equals 1. But when you plug fitness into there, if these W's are different, that means selection is happening. That means individuals with different genotypes have different odds, different probabilities of having babies. Okay, that's the definition of natural selection right there. Differential reproductive success. All right. So now when you plug in these fitness values, you get something that you plug them in like this, and you get something that isn't equal to 1, that we're abbreviating right now as W bar. That's mean fitness. You often indicate averages in statistics by a bar over a variable. So there's your W bar. All right. All right, let me give you the full equation and then actually work it. Let me tell you what we're going to do here. The way we get our predictions of what the genotype frequencies are going to be after 1 round of selection is we divide every one of these terms by W bar, right? You divide every term in an equation by something, right? That's basic algebra. So we divide every one of these terms by W bar. So we're going to divide that by W bar. And we're going to divide this and that by W bar. And what we get is that's all going to be equal to W bar divided by W bar. And that, of course, is equal to 1, right? Anything divided by itself equals 1. Okay, that's the equation that we want for making predictions of what the population is going to look like after 1 generation. After Dr. Shepard puts all of these fruit flies in some big jar and throws them a bunch of mashed bananas and let the fruit flies do what fruit flies do, what are the allele frequencies going to look like after 1 generation? All right. Think for a little bit before, we're going to finish this before we take a break, but think for a minute about what these terms here mean, and let's break them down. Okay, W big S over W bar, that is the fitness of the big S genotype divided by the mean fitness. If the fitness of this genotype is less than the mean, then that term right there, what I've just put in outlined in red, is going to be less than 1, right? Okay, if the numerator is smaller than the denominator, then the fraction is less than 1. So if the numerator is smaller than the denominator, that means the fitness of that genotype is smaller than the mean. And it means that after one round of selection, the frequency of this genotype is going to be equal to what it would have been without selection, which is just p squared, multiplied by something less than 1, right? And if you take a number and you multiply it by something less than 1, you get a smaller number, right? So right now, this is telling us that if the mean fitness is smaller, no, sorry, if the genotype's fitness is smaller than the mean, then the frequency of those individuals in the next generation will be less than it would have been if we had no selection. Am I kind of making sense? And then you can break it down the same way over here. 2pq is the frequency of heterozygotes if we didn't have selection. And then this right here, this ratio of fitness values, is how we model what happens if we do have selection. So if there's no selection, then the frequency of heterozygotes is just going to be 2pq. If the fitness of the heterozygotes divided is, okay, if the fitness of the heterozygotes is greater than the mean, then this term right here is going to be greater than 1, right? Because the numerator is going to be greater than the denominator, right? And if the numerator is bigger than the denominator, the answer is something bigger than 1. So if we take 2pq and we multiply it by something bigger, right? That means the frequency of the heterozygotes is greater than it would have been if we had no selection going on, right? If we had no selection going on, then this W big S divided by W bar would just be equal to 1, and it would just drop out. Because the frequency would be 2pq times 1, which is just 2pq. Yes? All right, but if the fitness of those heterozygotes is greater than the mean, then this quotient right here is bigger than 1, and the frequency of heterozygotes is going to be 2pq multiplied by something bigger than 1. So it's going to be equal to the frequency of heterozygotes without selection multiplied by something bigger than 1 that models the effects of selection. And finally, of course, we can do the same thing over here. Q squared, whoops, don't want to mess with that. Q squared is the frequency of homozygous recessives when there's no selection. And then you multiply it by this term. And again, if the fitness of that genotype is greater than the mean, then you're taking Q squared and multiplying it by something bigger than 1. So that tells you that the frequency of that genotype is going to go up. It's going to be larger than it would have been without selection. If, on the other hand, the fitness of that genotype is less than the mean, then you're taking Q squared and multiplying it by something less than 1. And that means you get something less than Q squared, right? It means that after one generation, the frequency of that genotype will be less than it would have been without selection. Okay, some people are looking at me a little bit cross-eyed. Let me try to show you how this works to solve the actual problem that we've got. Oh, I'm going to erase the formula below, if that's all right. Everybody got this? Or you need a second? All right. Okay. All right, so temporarily erasing all of that. What we want is going to be the frequency of alleles after one generation. And we already worked out that P, which is the frequency of the dominant stubble allele, we already worked out that that's 0.93. And Q is the frequency of the not stubble allele. And no, the frequency of the stubble allele is 0.07, and the frequency of the not stubble allele is 0.93. All right, we worked that out in part one. What is this population going to look like after one round of selection? Well, the equation that we started this mess with was p squared times the fitness of that genotype plus 2pq times the fitness of that genotype plus q squared times the fitness of that genotype is equal to W bar. All right, let's plug and shut. So to calculate W bar, okay, P squared is 0.07 times 0.07, and then the fitness of the corresponding genotype is 0. So of course that immediately drops out because anything multiplied by 0 is 0. And then 2 times 0.07 times 0.93 times 1. And then 0.93 times 0.93 times 1. And all that mess equals W bar. Okay, that's our mean fitness for the entire population. And that equals, those of you with calculators, get ready to punch some buttons. Okay, should be equal to 0.995. Okay, so it's close to 1, but not exactly 1. All right. Now what? Now we take this equation that we've got and we divide every term by W bar. We need more space here. And what that will do is give us an equation with 3 terms, each one of which is the frequency of genotypes after one generation of selection. All right. So what we get is 0.07, 0.07 times 0.07 times 0 divided by 0.995. That right there, that's going to be the frequency of homozygous dominance after one round of selection. So how many homozygous dominants will we get after one round of selection? 0, right? That 0 fitness right there pretty much negates everything else. So let me going back for a second to what I was talking about earlier. That 0.07 times 0.07, that's P squared, right? That's how many big S individuals we'd have if there was no selection. And then this 0 divided by 0.995, that is the effective selection. That's the effect that selection is having. And since it's equal to 0, it means that we don't get p-squared individuals with a big S genotype. We don't get any individuals with big S. Right? Don't exist. No existe. Sorry, I don't know what they don't exist is in Portuguese, but I'm fairly sure it's similar to Spanish.
Não existe.
No existe.
Não.
Now,
With the nasal.
all right, we want that. Now,
Não existe.
now existe. You know, I did actually travel to Portugal once, and it sounded a little different over there. I think Brazilian's softer.
Brazil is better.
Okay. I wasn't going to make that judgment call, but
Yeah,
Portugal's got really good wine. I'm not going to say anything bad about it.
they do. I'm moving there. Actually.
What's that?
I'm moving there.
Oh, cool. All right. Chit chat aside. So what we've got there is the frequency of big S individuals in the next generation, and it's 0. So now we divide this term by W bar, and that's going to be 2 times 0.07 times 0.93 times 1 divided by 0.995. All right, and let's make like MC Hammer and break it down again. No, I didn't want that. I want lines. All right. Draw. Color. There we go. That 2 times 0.07 times 0.93, that's 2PQ. That's how many heterozygotes we get without any selection going on, because that's just Hardy-Weinberg. And then we're multiplying that by 1 divided by 0.995. This is a fraction where the numerator is greater than the denominator. So I don't know off the bat what 1 divided by 0.995 is, but it's got to be greater than 1. Right? So we're taking the frequency of heterozygotes without selection and multiplying it by something that's larger than 1. That means that the frequency of heterozygotes will go up in the next generation above what it would be if we didn't have any selection going on. Okay, that's your measurement of the strength of selection that's tend to make genotype frequencies change. Okay, and if we plug and chug, 2 times 0.07 times 0.93 times 1 divided by 0.995 is 0.131. Okay, real quick, what's 2 times 0.07 times 0.93? What would the frequency be if we had no selection? Would be what, 0.1302. Okay, so it would be 13%, 0.13 frequency of heterozygotes if there wasn't any selection. Since there is selection going on, then the number is, what did you say the first one was?
0.131.
Okay, 0.131 without selection. With selection, 0.131. What is it without selection?
0.1302.
1302. Okay, so we get just a few more heterozygotes than we would if there wasn't any selection. It's the difference between 0.131 and 0.302. So it's a 0.1% change, but it is there. And then finally, to finish this off, we take Q squared, and that's 0.93 times 0.93. That would be the frequency of homozygous recessives with no selection. And then we multiply that by the fitness we've assigned, which is 1, and divide it by the mean fitness, which is 0.995. And yet once more, that right there, that's Q squared, that's how many homozygotes you have with no selection. And multiplied by 1.0995, that's greater than 1. So this is telling us we're going to have more homozygotes with selection than we would without. Okay, so just for fun, just 0.93 times 0.93, what's that? 0.93 times 0.93. That's what, 0.865. Okay, we'd have 0.865 or 86.5% of our fly population would be homozygous recessive without selection. All right, but now take that 0.865 and multiply it by 1 and divide it by 0.995. What do we get? .87. Okay, so we've shifted 0.5%. We would have 86.5% of our flies would be homozygous recessive if there's no selection. If there is selection, then 87% of our flies are homozygous recessive. So we've shifted by 0.5%. We have just a few more homozygous recessive flies than we would if there was no selection happening. And incidentally, the sum of all of those is W bar divided by W bar, which equals 1. Okay, questions? I'm still getting some looks that make it seem that I'm confusing half of the people in here, and I will make it clearer if I can figure out a way. Yes?
I think my question is, I believe is it just standard unless you do something for fitness, we just don't assume it's for that?
Okay. Let me make that clearer when we work part C. Okay. What you would, to calculate fitnesses, what you would do to calculate them is to get some kind of data on your chances of surviving. Like if this was a wild population and 25% of your stubble flies survived without getting eaten by spiders, but 36% of your normal flies survived without getting eaten by spiders, you could use that to calculate fitness. You could say, okay, the survival of stubble flies is 0.25, and the survival of non-stubble flies is 0.36. And then you would just divide those by the greater of all of those. So the relative fitness of the normal flies would be 0.36 divided by 0.36. And the relative survival of stubble flies would be 0.25 divided by 0.36. Let me reintroduce that when we work the last part of the practice problem. Okay, I might be able to make that more clear. Yes?
And the relative fitness proportions is always just going to be 0 over x and x over x like that? Or
No, we set that up, we set this up the way we did because in this particular case, big S genotype is an embryonic lethal. So the fitness is always going to be 0 because flies with that genotype are never born. They never reproduce because they don't exist.
And the other ones, like I understand that one, and the other ones just, they'll always be x over x equals 1.
Let me address that when we look at the third part of the problem. I think I can make fitness calculations a tiny bit clearer here. Okay, anything else? Did you folks use a break? What the heck, I could.
Was that all B or was that just the main fitness part?
Yeah, that should be, that should be all of B, calculated the mean fitness. And then each of these terms of the equation that we got corresponds to the expected frequency of a genotype after one round of selection.
So the 0.130 is 13%, represent 1%.
Yeah, what I've outlined here in yellow, all that is the expected frequency of heterozygotes after one round of selection. And what I've outlined in green is the expected frequency of homozygous recessives after one round of selection, after one generation, basically. So yeah, we're doing science here. We can make predictions of what we ought to see. And then we can test those predictions by actually going out and raising a bunch of fruit flies. All right, I'm gonna go get myself some caffeine. Maybe that'll help matters. And I've got 10:07, so we'll reconvene at 10:20. And I will